We're going to talk about momentum. Momentum, a lot of you are probably already familiar with. You've used the word before, you've heard the word before, but a lot of you would probably have a hard time describing it. So to start, I want you to think of momentum as how difficult it is to stop a moving object. It's not 100% correct, but it's kind of correct. But I want you to think of it that way for these three pictures, for this first example. Which of these objects would be the hardest to bring to a stop, the most difficult to stop? Go ahead and pick out the easiest one first. I would think the easiest one to stop would be this person over here. They are not moving, so it would be easiest to bring them to a stop because they're already stopped. A lot of you probably would also think that this person doesn't have any momentum because a lot of you think in the back of your minds that momentum has to deal with a moving object. And you're right, it does. So this person has no momentum. However, these other two examples are both moving. Which of these would be the most difficult to bring to a stop? I would say the kitten would be much easier to bring to a stop than the sumo wrestler, because the sumo wrestler is way bigger in size than the kitten. The sumo wrestler is much harder to change or to stop because it's bigger. Let's look at an example where the two objects are relatively the same size. So we have Phoebe in the green, who's running much faster than Rachel in the blue. Let's assume both of these ladies are about the same size. Which would be harder to bring to a stop? Who has more momentum? I would say Phoebe. Phoebe is moving much faster than Rachel. She's therefore further away from rest and would be harder to bring to a stop. You would have to work harder to bring Phoebe to rest than you would Rachel. Rachel's moving pretty slow and kind of close to being at rest. So with these two examples that we just talked about, we kind of figured out the equation for momentum, what momentum is made up of. It depends on your size, and it also depends on how fast you're going. So the equation for momentum is actually P, and P is the symbol for momentum. M was already taken for mass, so they went to the next logical letter, is equal to mass times velocity. It directly depends on both of those things. The more mass you have, the more momentum you have, and the more velocity you have, the more momentum you have. If you want to know what to measure momentum with, mass is measured in kilograms, velocity is measured in meters per second. Kilograms times meters per second will be kilogram meters per second. So before in this first example, we talked about how mass, the more mass an object had, the harder it is to slow the object down. There's an idea or a word for this idea. The more mass you have, the harder it is to change an object. And that is this idea of inertia. I want you to think back to the law of inertia that we talked about a few units ago. It's Newton's first law. An object in motion continues that same motion, or an object at rest stays at rest unless acted upon by an unbalanced force. Momentum is specifically talking about the first half of this law. An object in motion continues that same motion unless acted upon by an unbalanced force. So I want you to think of momentum as moving inertia. It is still this idea of inertia, but only applied to moving objects. The bigger you are, the harder it is to speed you up or slow you down. And the faster you are, the harder it is to speed you up or slow you down to change your motion. Great. So now I want to talk about driving for a second. A lot of you are learning how to drive, or maybe have been in the car with somebody driving, or maybe you already have your driver's license, but you've probably noticed people on the road who don't come to a complete stop when approaching a stop sign. Why do people do this? Why is this such a big deal? Why do people not want to come to a stop at a stop sign? A lot of you are going to say, well, duh, you don't want to lose momentum, which is correct. But a lot of you have a hard time describing momentum, so let's think of it some other way. Why don't you want to lose that momentum? What's the big difficulty with losing that momentum? The answer is a lot of you, or I shouldn't assume it's you, it's a lot of bad drivers, are lazy. They don't want to exert any effort or force into bringing their car to a stop By pressing on that brake pedal, right? To come to a complete stop, you have to exert a force, which means you have to exert effort. And a lot of you are lazy and don't want to do that because let's say you're moving. It takes a certain amount of force to bring you to a complete stop. And then even more annoying, you don't just stay at that stop sign forever, you have to get back up to moving again, which means you have to apply a force, this time on the gas. So you're exerting a lot of effort, and a lot of you are lazy and don't want to do that because in order to change your speed, you need to apply a force, which you might remember this equation from an older unit. Any change in motion is caused by a force. But since I'm changing my speed or my velocity, we also learned that we would be changing our momentum. We are losing and gaining momentum. So let's talk about that for a second. We want to change our momentum. Symbol for change is delta, and then symbol for momentum is P. Which part of this momentum equation do you think we are changing, the mass or the velocity? The answer is it could be either, but if I change my mass, I'm changing the object I'm talking about. And we're not going to talk about that very often in this physics class, but it definitely does happen in like car accidents where bits of car fly away or get greatly damaged. The mass changes. In this class, we're just going to focus on changing velocity. So we're changing our speed. And we agreed earlier that to change our velocity or to change our momentum, we need a force. So I'm going to show how these two equations are related by rearranging this force equation over here. So I'm going to rearrange this just slightly. I'm really just going to replace the acceleration with its equation. Acceleration is a change in velocity divided by time. So now it's starting to look more like momentum, but I need to get rid of this time right here, this pesky time. So I'm going to multiply by time, so it cancels on this side, but what I do to one side, I have to do to the other. So here is a brand new equation, and would you look at that? This side of the equation is the equation for change in momentum. So I can say that the change in momentum is equal to whatever this side of the equation is, force times time. There is a name for this side of the equation, and it's called, or a symbol, it's called J, and J is the symbol for impulse. They use J because I is used for inertia in more complicated physics equations, but you can think of it as impulse or impact. And the equation for it is force times time. And really, it's just saying that your change in momentum is directly affected by how much force you apply, which you know is true, and how much time you apply that force for. So for instance, if I apply a lot of force, I can change my momentum more. If I push or pull on an object for a long period of time, I can change my momentum even more. So I don't know if you recognize this or not, but a lot of math equations I know look like gibberish, but they're big ideas written in symbol form, written with shorthand. So this equation is on your formula sheet, and you're rarely going to use it for math. It's an idea, okay? And this idea is just that any change in momentum is directly related to or is exactly equal to the amount of impulse you apply on the object. It's exactly equal to how much force times how much time you apply that force for applied to the object. So impulse is directly related to change in momentum. That's an idea equation. This equation over here, you're going to use most often for math because we have ways of measuring force, time, mass, and velocity. Great, I have another example for you. Let's say you're in an out-of-control car moving 50 kilometers per hour and your brakes fail. You need to stop. So you have a brick wall in front of you and a giant haystack. Both are capable of stopping you. Which of these two objects would you choose to hit to slow you down? Let's look at it this way. In both of these situations, my initial velocity is 50 kilometers per hour. And after hitting both of these objects, my final velocity would be 0. The difference, a lot of you would pick the haystack, and you would be right. But the difference between these two, and a lot of you would say, well, the other one's softer. Let's say I'm driving and then I hit the brick wall. It brings me to a stop immediately. Versus if I'm hitting this haystack, I'm going to hit the haystack, but I'm not going to stop immediately. It's going to take me some time to go through the haystack to finally bring me to a stop. So here with the brick wall, I hit it and I stop immediately. So I feel the full force needed to bring me to a stop all at once, which would hurt. Versus here, I start to stop the second I hit that haystack, and then I gradually come to a stop going through the haystack. The big difference between each of these situations is the brick wall stops you all at once. It does apply a lot of force because there's very little time to stop you. It stops you all at once. Versus the haystack takes a long amount of time to stop you and therefore spreads that force out so that you don't feel it hit all at once. In both of these situations, the change in momentum is the same. Because change in momentum is mass times velocity. It's the same car in each situation. And in both situations, you're going from 50 to rest in each situation. So your change in momentum is the same, which means that impulse is the same. We learned from that last equation up here. So if change in momentum is the same for both, impulse is the same for both. But if I increase time of impact, I can actually decrease that force because this whole number ends up staying the same. I also like to think of this as braking cars, like when you're stopping your car. I used to think when I was learning how to drive, I was kind of a ditz, and I used to think I needed to apply the brakes right when I was next to the stop sign if I wanted to stop. But if you're right next to the stop sign, you have to hit that brake pretty hard. You have to use a lot of force because you have very little time to stop your car. If you want that gradual, very easy stop, you need to start braking far away. You need to apply the force far away and take more time to stop. That way you don't need as much force. You don't have to press on the brake very hard to stop your car. The last example I want to talk about is this activity you should have done over the long weekend. You were supposed to make a contraption that would catch an egg. And this egg would hopefully survive a fall. So these two examples are a plate or a pillow. We'll call them A and B. And we'll say A was an unsuccessful contraption and B was a successful one. The big difference between whether or not your egg, the goal, I guess, was you wanted to decrease the amount of force. I drew the arrow backwards. Decrease the amount of force you want acting on the egg. You don't want to break the egg. The idea behind this is you want to increase time of impact. This pillow takes a longer time to stop the egg. It starts stopping it the second it hits the surface, and then it has a little give and takes a longer time to stop it. Versus this plate over here stops it all at once. It has a very short stopping time, so therefore applies a lot of force. If I increase time of impact, I decrease the force acting on my egg and hopefully don't break my egg or whatever object you chose to drop.